Hello, good morning everyone. Myself I am Jagat. Here is a project of real-time EV monitoring and ADAS dashboard system presented by Jagat, Department of Electronic Communication Engineering, Institute Paul College of Engineering and Technology, Coimbatore. Industry partner Emergence Technology. Here we are going to see the introduction. Uh, Nowadays, electric vehicles are becoming more popular. To make them safer and more efficient, drivers need real-time information about the vehicle emissions, like vehicle speed, battery level, ultrasonic sensor, acceleration. In this project, we use STM32 Blueprint microcontroller to connect the import data such as like that's already I told vehicle speed, battery level, ultrasonic. STM32 sends data through UART serial communication to computer. A Python dashboard display the information real time and updates about 10 every second, 10 hertz. And again, we are going to see next project objectives. In the project objectives, we are going to see primary objective. Our main goal is to design a EV monitoring system that continuously measures the vehicle performance and improve driver safety in online without using any physical components. On-chip modeling. On-chip modeling means this project performs calculates directly inside the extended microcontroller. It estimates vehicle acceleration, braking behavior, battery state of charge (SOC), which indicates the remaining battery percentage. Next, ultrasonic data grid. Here we use the ultrasonic sensor for measuring the distance. We use three ultrasonic sensors placed around the vehicle, right side, left side, and front or back. Yeah. These sensors help provide forward collision warning and blind spot direction. Once the forward collision warning alert the driver if an object is too close in front. If any object is too close to the driver, it will detect. And blind spot detection warns the driver if another vehicle or object is in blind spot. Telemetry and user interference. All the collected data is sent through UART conversion to Python dashboard. The dashboard displays the important information such as speed, battery percentage, obstacle duration, safety alerts. Okay, next we are going to see hardware software technical stack. How means the main controller is STM32 F103C8T6 Blueprint microcontroller. It feeds analog signal using its 12-bit ADC, which converts analog value into digital value from 0 to 4095. For interrupts, we use potentiometer. Throttle, brake, battery state of charging, called SOC, motor temperature. We also use the three ultrasonic sensors to detect the obstacle around the vehicle. For output, we use 4 LED to indicate different system conditions. PWM control buzzer to provide different warning sounds depends on the charger level. The firmware is developed using STM32 IDE and STM32 QLED. We use STM32 IDE and next operational parameters and threshold logic. In this section explains how the system works and when it gives a safety warning. The STM32 reads sensor value using 12-bit ADC and sent through UART communication. Here we are using UART communication. UART communication only we can use with broad rate because it does not have any clock signal. SPI2C only uses clock signal. UART only uses broad rate like 11,000, 5,000, 1, 115200. The dashboard receives updated information every 10 milestone, giving a refreshment rate of 10 times per second. The simulator vehicle support speed from 0 to 200 km, motor torque up to 250 Nm. These driving modes echo normal sport. The ADAS safety feature include forward collision warning. If an obstacle within 50 cm, the system gives warning. It comes closer to 20 centimeter, a critical alert is generated. That means 50 centimeter means warning will come. If the vehicle is come from 20 centimeter, this means a distance, it will generate a alert generated system. Blind spot detection, BSD. If an object is detected within 30 centimeter, while the vehicle speed is about 20 km, the side warning indicator turns on. They are telling that if the vehicle is 30 centimeter, 30 centimeter from our vehicle, and we are in 20 kilometer speed, the indicator will turns on the warning signal. Then thermal protection. In the motor temperature exceeds 80 degrees, the system enters protection mode to prevent damage. Next, we are going to see system architecture and data pipeline. Here is system architecture. And this section explains how data flows through the system. That means how the data sends from simulator, blueprint, intelligent system, Python dashboard. A sensor. The throttle brake, battery level, and temperature values are generated using potentiometer. Ultrasonic sensor detect nearby obstacles. Step 2. That means STM32 processing. The STM32 reads all the sensor data using ADC and ultrasonic timer circuit. And also the STM32 processing will calculate the vehicle speed, battery status, distance to obstacle, collision risk. Vehicle speed, how much the vehicle is traveling, battery status, how much the battery is remaining, and also distance to obstacle. Then means in our car, we are in our car, and the opposite and the obstacle is how much in the distance. And collision, collision means we all know. And this step 3 telemetry. The process data is converted into text package and transferred through UART at baud rate of 115200 bps. Step 4 Python dashboard. The Python application receives the data using PySerial. Here we are using PySerial that will receive the Python dashboard details about display. What are this Python dashboard display? Speed, potential speed meter, battery percentage, temperature, ADAS radar, warning messages. The dashboard updates smoothly for at 10 frames per second, giving real-time monitoring. Next, we are going to see outcomes, validation, and verification tests. How much? Hardware and software integration. STM32. How hardware and software integration? STM32. The STM32 successfully processed sensor data while running the ADAS algorithm without affecting system performance. Low latency performance. The data transmission through UART was stable at 11520 bps with no data loss, and the dashboard updated smoothly. Dynamic responders. Speedometer responded instantly when the throttle changed. When the brake was applied, the system simulated regenerative braking, just an electric vehicle. Safety interlock. When an obstacle entered the warning zone, the dashboard changed color immediately and the buzzer sounded to alert the driver. Thermal protection. When the simulated motor temperature exceeded about 80 degrees, the system generated a fault condition, stopped the motor output, and turned on the fault LED.
Okay, before this we have seen what is EVATA system in that paragraph. Now we are going to see the simulator. Here we have see the simulator. We configure the IOC file. IOC file. In this IOC file we are using STM32F1003C86. We configure all the pins and all the pins as digital pin, analog pin, timer, counter pins after generating. We program for this microcontroller. All means this the all ports we are used in the program ADAS EV everything. Here we used after compiling the program without error, we generate the project. This is the program we compile all the projects. That means all the ports and everything we have compiled all this, and we will open next step. Next we will go into opening the Pixim lab. Before going to Pixim lab, we can see here down the program. Next Pixim lab. Next we are opening the Pixim lab, simulating for showing the output. This is the Pixim lab. We have generated the coding. We have done all the projects in STM32, but use this Pixim lab for showing the output. Pixim lab simulator for showing the output. Next here we choose the microcontroller that we using project. What the microcontroller we use? STM32, and we
Use combined in STM32. Bin file STM.
Cube IDE, and we add the spare parts in this project, and we add the all spare parts: ultrasonic sensor, potentiometer, LED inductor, ultrasonic for distance, potentiometer for unlock pins. And next we will open the visual terminal. Wow, what we want visual terminal? Why we want to open the visual terminal? Means visual terminal is only shows the output of the project. Here we see the car speed, torque, acceleration, pressure of the range, and battery, brake, front, everything. That means not seeing visuals. That means output of this battery project, like then we can see is in visual. That means visual terminal, that is the output. And left distance and blind collision, and also successfully connecting all those parts in Pixim lab. Next we are going to see what means USB tool. USB tool, not that's a tool called VSB tool, connecting ports as common COM3. Here we are using the VS tool, means common and COM3. Virtual helps to connect the simulator. Opening Python dashboard. Python dashboard. Flash code to COM3. Here we are flashing all the code to COM3. After opening the Python dashboard working project, shows the distance of front collision 340 centimeter and reduce the front below 150. Wait, I will tell. Now it's showing the VSB tool. Next I will yeah, here only it shows the total distance of this ultrasonic sensor 340 centimeter, but if we reduce it to 350 centimeter, what will happen? Because what will happen, it will happen when the if we reduce the distance from 340 centimeter to 140 centimeter, the ADAS E project will shows the alarm for distance is below. Wait, it will see how the distance 150. See here what's showing, it shows alarm. Wait, it's showing. Oh yes, it's showing. No, it's a alarm. For what? The collision other obstacle is near to us. This is it's showing. When it shows uh, when it's moving, it started to move. It started to move. Here we use the car speed increasing. Now we are going to increase the car speed. See, it's increasing 68, 76, 86, 97, 180, like that 188, 129, 140, 139. So yes, it's now it will decrease because I apply brake. Why I use here brake? Brake is used to reduce the speed, because the car, when you give accelerator, the car will move, grow. The car speed will increase more and more increase. The maximum car speed is 25. Again I am giving accelerator here. 89, 103, 106, 130, 140, like that I am giving. The maximum speed is 200, like it will go. It will never go after 200. I will give accelerator more speed, apply brake. Why I use here brake means brake to reduce. Now the top speed is applied. Okay, the alarm is alarming because the car is too far. Apply speed. Apply brake. Sorry, apply not speed. After applying speed, we use again brake. Brake. Why means brake means to reduce the speed. Here it's reducing the speed 186, 19, 179, 172, 164, 158, 150. 142, 133, 12, 125, 116, like that reducing. When I give the accelerator speed, the battery will reduce normally, because it's EV car now. Because when I give accelerator, the battery power will reduce gradually. Is 200 km/h total speed. It shows the torque of the car. Here down we can see that car torque, temperature, accelerator, brake, alarm, fault signal, like that all. And below, next we are applying the temperature. What is going to happen when I apply temperature? Next we are going to see. Now we can see what's happening here. Yes, temperature. We are going to give temperature high means what temperature will high. To collision we find, it shows alert in sensor. If a car is going 20 km per hour, 20 km per hour, if the obstacle is come in front of you, what will do? The obstacle will come from that means the car ultrasonic sensor will uh, give me a alert signal for alert. That means front, left side, right side, or every side it will give you alert for you. Okay, this is the total project I have done in emergency technology.